The observation that orbits are conic sections actually predates Newton and was first published by Kepler, who based this finding on analysis of naked eye observations of Mars performed by Tycho Brahe. Kepler found that the orbit of Mars was best fit by an ellipse with the sun lying at a focus and could not be readily described by a circle, which was the predominant theory at the time. Kepler continued his work using observational data and eventually postulated two other laws. The second one being that a line segment joining a planet and the sun sweeps out equal areas in equal time. And the third and final law being that the square of the orbital period is proportional to the cube of the semi-major axis. We have already demonstrated that the Newtonian analysis directly leads us to the conic section equation, which is law 1. We can also use our mathematical tools to find the other two laws. The utility of these laws is that they give us a very, very strong geometric understanding and intuition for what is happening in the two-body system. And so it's very much worth our while to not only derive them, but to explore them in detail. Possibly the most intuitive understanding of a conic section is as the intersection of a plane with a cone. As shown here, by intersecting planes at different angles with the cone, we produce different geometric figures. A plane that's parallel to the base of the cone produces circles of different sizes. A plane at an angle with the base produces ellipses, and a critical angle that matches the angle of the size of the cone produces a parabola. Everything lying outside of the regime of the ellipse and the parabola becomes a hyperbola. And if you extend the mirror image of this cone upwards, this plane will eventually intersect the upwards cone and will produce a mirror image of this hyperbola on the other side. So hyperbolae always come in pairs. There are many other methods of parametrizing conic sections. Another one is based on defining three components: a focus, a directrix, and the eccentricity of the conic section. The directrix is a line lying outside of the conic section with a height drawn through the focus, making a right angle with the directrix. We can draw a line segment between the focus F and any point on the conic section P. The ratio of the length of this line segment FP to the line segment PQ, which is a height from the point on the conic section to the directrix, is given by the eccentricity E, such that the length FP is equal to E times the length PQ. An ellipse has eccentricities defined between 0 and 1, and a circle can be thought of as a special case of an ellipse with an eccentricity of 0. A parabola has an eccentricity of exactly 1, and a hyperbola has an eccentricity of greater than 1. The conic section can be thought of as the locus of all points for which this geometric relationship holds. So let's take these shapes one at a time and start with ellipses. An ellipse can be parametrized by the equation r prime plus r is equal to 2a, where r and r prime are the distances between any point on the ellipse to the two foci of the ellipse. In the general case of the geometric figure, there's no real distinction between the two foci, but when we're using this geometric framework in order to describe orbits, there's a significance to one of them, because you'll recall that the central body lies at one of the foci of the conic section. So we will call the filled focus F, that is where the central body of our orbital system lies, what we previously called point O, or the coordinate origin of the parafocal frame. And we will call the point F prime the vacant focus. It is the other focus of the conic section that is geometrically special, but has no physical significance in the two-body system. It is just a piece of geometry. The semilattice rectum, or semiparameter, L, is the height above each of the foci to the ellipse. And this is the L that we've previously defined as the numerator of our conic section. This expression, R is equal to the semiparameter divided by 1 plus the eccentricity times the cosine of nu, applies to every single conic section. And from this, we can match L to h squared over mu, which is the value that we derived starting with Newton's laws and Newton's law of gravity, and we can set these two equal, again, for all conic sections. This first expression is specific to the ellipse. That tells us that for the case of the ellipse, the semiparameter is equal to the semi-major axis times 1 minus the eccentricity squared. The semi-major axis is the length from the geometric center of the ellipse along its major axis, and the semi-minor axis is the distance from the center of the ellipse to its edge along its minor axis. B is the smallest extent, A is the largest extent. We can further define a linear eccentricity, C, which is equal to AE. Let's explore some of these results in a little bit more detail. We start with this parametric expression, R prime plus R is equal to 2A. Remembering that 2A is the total distance along the major axis of the ellipse. Let's consider the case where nu is equal to 0. In this case, we have this segment FP lying along the axis, measured this way, and the segment F prime P, or what we're calling R prime, lying along the same axis so that it lies on top of R. In this case, we can then write, and you'll notice that this AE term is what we have already defined as the linear eccentricity. That is the distance from the center to the focus. This simplifies to A times 1 plus E. We can then solve for R, which is our orbital radius, and find that in this case, it'll be, so in the case where nu is equal to 0, the orbital radius will be equal to the semi-major axis of the ellipse times the quantity 1 minus the eccentricity. You will recall that this case of nu equals 0 corresponds to what we've previously defined as a turning point, when the orbital radius vector is parallel to the eccentricity direction, which lies along this line. We can also think about the opposite case where nu is equal to 180 degrees or pi radians. And in this case, we will get the result that R is equal to A times 1 plus E. Because these are special points, because these are turning points, we give them specific names. This turning point is called periapsis, and this turning point is called apoapsis. Periapsis is the closest approach of the two bodies, and apoapsis is the most distant separation on the whole closed orbit between the two bodies. From this, we can also get another expression for eccentricity, solving. Therefore, if you know the periapsis and apoapsis of an ellipse, you can instantly calculate its eccentricity. Just a very quick note on nomenclature, the ending of the term is often changed when there's a specific central body. So when you're talking about the closest approach to the sun, you will talk about perihelion, from the Greek helios for sun. When you're talking about the closest approach to the Earth for an Earth orbiting spacecraft, you will talk about perigee, and so on. Closest approach to Jupiter will be perijove, while furthest separation from Jupiter of a spacecraft orbiting Jupiter will be apogee. For an arbitrary star, we often say periastron and apastron. But periapsis and apapsis or apoapsis are very general terms that you will often come across. We can also evaluate the semi-minor axis based on the geometry of this ellipse. We get the result that b squared is equal to a squared minus quantity a e squared, just by forming the right triangle with whose base is c. And that means that we can again calculate that e squared is equal to 1 minus quantity b over a squared. Next, if you apply the law of cosines to the triangle defined by f prime p f, then we can write r prime squared is equal to r squared plus quantity 2ae squared plus 2r times 2ae times cosine of nu. And we've already established that this quantity is the same as 2a minus r, quantity squared. If you chug through the algebra, you will find that this gives us the first expression on the slide, that the orbital radius is given for an ellipse as a times 1 minus e squared over 1 plus e cosine of nu, and therefore, for an ellipse, the semi-parameter is a times 1 minus e squared. So these are incredibly useful relationships. A times 1 minus e squared is equal to h squared over mu for an ellipse, And for all conic sections, h squared over mu is equal to the semiparameter. Finally, we can define the focal parameter, which is the distance between a focus and the directrix, and the directrix is symmetric to either side and parallel to the semi-minor axis. And just a quick note of caution, in many, many texts, the P and L parameters are reversed in definition. And so lots and lots of literature will have the semiparameter defined as P and the focal parameter defined as L. But in our case, we are defining L as the semiparameter and P as the focal parameter, and P is equal to L divided by E. These same basic definitions apply for both parabolae and hyperbolae. The only caveat is that the semi-major axis is undefined for a parabola that has an eccentricity of exactly 1. And so in this case, we will repurpose the A parameter to be the focus to periapsis distance, and also the periapsis to directrix distance. For a hyperbola, the definitions are all exactly equivalent. And of course, there's always a pair of hyperbola, one about the filled focus and one about the vacant focus. But the definition of semiparameter and linear eccentricity and focal parameter are all effectively the same. So in your handout, there's just a table summarizing all of this information and giving the basic equations in Cartesian coordinates for the various figures. And again, the only thing to be careful of here is that in the case of a parabola, we are redefining A as the focus to vertex distance because the semi-major axis is effectively undefined and the linear eccentricity is infinite. You can also think of the semi-major axis as being effectively infinite because the equations break down in this one case. So that was Kepler's first law, and its primary utility is in giving us a very solid geometric description of what is happening to objects on these orbits, on these conic sections. But Kepler's second and third laws are actually much more useful in terms of performing actual computations about what happens on these orbits. And it turns out we can directly derive these from results that we have already derived by way of exploring the Newtonian solution to the two-body problem. And so we start with this previous observation that we made that r nu dot is equal to the ratio of h to r. That is, the orbital radius magnitude times the scalar time derivative of the angle nu, which is called the true anomaly, is equal to the ratio between the magnitude of the angular momentum to the orbital radius. From this, we can think about a differential area element. So here we have an infinitesimal change in nu, which we will call d nu, leading to a swept out area dA, and it will have an arc length along the orbit of r d nu, which takes us from a point p at time t to the point on the orbit at some infinitesimal time dt later. Geometrically, we can describe this differential area element as 1/2 of r times r d nu, 1/2 of the base of the arc times the arc length, which we can then rewrite as 1/2 of r squared d nu dt dt, taking advantage of the usual calculus operation of multiplying out differentials. And this we have already defined as h from this relationship. So this relationship is what allows us to make this substitution. We move the dt over to the dA side, and we get dA dt is h over 2. H is a constant, and therefore what this statement is actually telling us is Kepler's law. Equal areas in equal times. The corollary to Kepler's second law is that the orbiting body is moving the fastest when it is at its closest approach to the focus, and it's moving the slowest when it's furthest away. When it is here at periapsis, the body needs to sweep out a much larger arc length to cover the same area as it would over on the other side at apoapsis, where a very, very small arc length will produce the same area because of the much longer orbital radius. And the larger the eccentricity, the more pronounced the effect. For a circular orbit, the velocity is constant. The orbiting body is moving at constant velocity everywhere on the orbit. For very high eccentricities, the body is moving incredibly fast at periapsis and incredibly slow comparatively at apoapsis. And so here we have the mathematical statement of equal areas and equal times. We then take this expression and we integrate it between 0 and the orbital period of the orbit, which we will call T sub p, which means that we are integrating h over 2, which means that the area swept out over a full period is equal to h over 2 times Tp. You will recall that the area of an ellipse is given by pi AB, where A is the semi-major axis and B is the semi-minor axis, which, based on our previous geometric derivation, we can convert to pi times a to the 3/2 times the square root of the semi-parameter, which all must be equal to h over 2 times the orbital period. And here we have the mathematical statement of Kepler's third law. Kepler stated that the orbital period was proportional to the semi-major axis to the 3/2 power. And he was absolutely correct. We now, with the help of Newton and our earlier derivations, can fill in the constant proportionality and know it to be 2 pi divided by the square root of the gravitational parameter. Remember always that the gravitational parameter is the sum of the two masses times the gravitational constant. Many times, this is approximated as just being the gravitational constant times the more massive of the two bodies. So for example, if you're talking about a spacecraft orbiting the Earth, you might just use the gravitational parameter that is the gravitational constant times the mass of the Earth, ignoring the mass of the spacecraft because it is so small in comparison to the mass of the Earth. And for a numerical approximation, that's usually just fine. But formally, the gravitational parameter is always the gravitational constant times the sum of the two masses. And as the two masses approach each other, as you're talking about, say, binary stars or stars and large gas giant planets, then it becomes a not insignificant change to ignore the mass of the orbiting body.